Hi, everybody. I'm Azusa. I'm a postdoc in Toulouse, France, working with Chen Wang. He's my advisor, and he is the MOPCA laureate under the project name EuraAce. And today, I'm very excited to share my ongoing work addressing the question as to if we can machine learn the raindrop formation processes or not. And I'd like to thank Chen for giving me this opportunity. And you can start the presentation and go to the next slide. Yeah, so I know we've already had a few presentations or talks focusing on clouds. So I'm going to very briefly talk about the importance of clouds in the climate system here. So according to some study, more than half of the globe is covered by clouds on average. It can vary anywhere between 56 to 73%, roughly speaking. And of course, this coverage changes depending on the region, depending on the year, depending on the season. But on average, we can say half or more than half of the globe is covered by clouds. So you can imagine a significant impact of clouds on the radiative balance at the surface and also at the top of the atmosphere, both in terms of short wave and long wave radiation. Also, a very small fraction of clouds can actually precipitate. And once those clouds provide precipitation to the ground, that is an excellent way for the atmosphere to transfer energy from the lower troposphere to the upper troposphere. And sometimes it can even lead to an extreme precipitation events and cause floodings. And those extreme events have severe impacts on our lives and are important as well. So clouds, because of their impacts on radiation, also dynamics, they are a key factor in the climate system. And you can go to next. So today I'm going to talk about cloud microphysical processes. So this is a schematic figure from Morrison et al. 2020, and you can see a number of processes, microphysical processes involved in a convective cloud. And first of all, there are a number of processes involved. That's one of the reasons why modeling cloud microphysical processes is very complicated. And each of these processes needs to be parameterized differently and separately. And even though there are a number of processes, some processes may not even play an important role in certain types of clouds. So that is also another factor that's making the modeling of cloud microphysical processes difficult. I also want to point out that there are some anthropogenic impacts on clouds through aerosols. So this so-called aerosol cloud interaction has been drawing a lot of attention over the past few decades. And IPCC actually names this aerosol cloud interaction as one of having the largest uncertainty in the climate system in terms of radiative forcing. And so aerosols can impact clouds because cloud droplets, once air gets saturated, those supersaturated water vapor needs some surfaces to condense onto, and those surfaces are aerosol particles in the atmosphere. But depending on the aerosol types, chemical compositions, and sizes, those cloud condensation, water vapor condensation can be a little different, and that can impact the entire cloud properties afterwards. And another complication is the measurement difficulties. So what we can measure is mass number concentration or number concentrations. Sorry, mass concentrations or number concentrations, but they are just the product of all those processes or just one process. So it is very difficult to actually deduce the process rates from observations. And we can do lab experiments, but we are not, sometimes these lab experiment results do not necessarily apply to the real atmosphere under certain conditions. So those are some factors that make cloud microphysical processes and their modeling very difficult. So if you click next, I think there is another figure showing up. Yeah, so that's also from the same paper. showing schematically how cloud microphysical processes are modeled in different models. You can see here 6 water species or so-called hydrometeors included in numerical models. That this number of hydrometeors can vary anywhere between 1 to 6 or 7. And you can see cloud droplets, raindrops, water vapor, etc. And each of these processes among those hydrometeors are calculated separately in microphysics schemes. But in reality, a lot of times there is often no clear separation between different hydrometeors. So, cloud droplets are small, but they grow in size gradually, and eventually they fall to the ground as rain. But sometimes in models, we need to make a clear separation between liquid clouds, liquid droplets, and raindrops. So that's another difficulty in cloud microphysical modeling. And today, if you go to the next slide, we're going to be focusing on only cloud droplets and raindrops among all the other hydrometeors. So I want to just briefly explain how they form, and starting with aerosol particles. So aerosol particles are small particles in the atmosphere. A lot of them are sized around 0.1 micrometers, or it can be hundreds of nanometers. But it can really vary anywhere between nanometers to tens of micrometers. So there are different kinds of aerosols. They're different in sizes, chemical compositions, distributions, and abundance as well. Like I said earlier, once air gets saturated, those supersaturated water vapor condenses onto aerosol particles, and eventually they grow large enough to be called cloud droplets. And this process is called activation. And typically, cloud droplets are sized around 10 micrometers or so. And if there are enough cloud droplets in the atmosphere, if you click next, they can form raindrops. As I said earlier, not all clouds form rain. And these raindrops are much bigger and much fewer in number concentrations, and the diameter is typically around 1 millimeter or so. And this growth from cloud droplets to raindrops just happens within 20 to 30 minutes. And there are 2 key microphysical processes responsible for this growth. One is condensational growth. So the supersaturated water vapor condenses onto existing small cloud droplets and make them larger and larger. And the other is collision coalescence. So as this name suggests, existing small cloud droplets can collide with each other, make a larger cloud droplet, and that gets repeated until raindrops form and eventually fall to the ground. So I call these processes warm cloud processes because they don't involve any ice phase, ice crystals, or snow or ice phase hydrometeors. And the topic of today's talk is this parameterizing warm cloud processes. So if you can go to the next slide, here I'm trying to explain how raindrop formation process, or the conversion process from liquid droplets to raindrops, are parameterized or represented in different kinds of models. And from left to right, I'm increasing the spatial and temporal scales resolved in those models. And I'm starting with a Parcel model. So I know there is also direct numerical simulations, but today I'm going to be starting with a Parcel model. And then the process that is resolved by these models are often on the order of centimeters. And for the calculation of raindrop formation processes, they use this equation, so-called the stochastic collection equation, that is able to calculate certain size of cloud droplets interact with certain size of cloud droplets, and then what's the likelihood of that, and all those complex interactions between 2 different sizes of cloud droplets. And I wrote here microphysical because these parcel models often are purely microphysical, and sometimes, a lot of times, they don't involve any dynamical components, meaning that they're not impacted by surrounding dynamical conditions. Sometimes it does, but a lot of times no. And so the microphysical processes, or this raindrop formation process, is calculated through this BIM microphysical calculation, meaning that the size distributions of cloud droplets or raindrops are represented by tens or hundreds of bins. Each bin represents a group or population of cloud droplets having the same size. And this bin microphysics can calculate how each bin interact with the rest of the other bins, and then how the mass concentration or number concentration in each bin changes after interacting with all the other bins. So these are very sophisticated calculations and also computationally very expensive. There's also a large eddy simulation, or large eddy simulations, LESs. They are a little more coarse, but they are typically able to resolve large turbulences or eddies, and the scales are tens of meters to hundreds of meters. But because of their scales, now they cannot afford computationally this thin microphysical calculations, and a lot of times they include bulk microphysics. This is also the case for, if you go to the next slide, also case for the cloud resolving models, or CRMs, that are often used for weather forecasting. So now the scales resolved are hundreds of meters to 5 kilometers or so, roughly speaking. And as the name suggests, they resolve clouds. They're able to resolve not just stratiform clouds, but also convective clouds. But because they cannot afford this BIM microphysical calculations, they instead use bulk microphysics calculations. And in terms of raindrop formation, they use approximate estimate or estimated calculations of rates. So that is called parameterization. So if you give a certain condition, surrounding conditions such as temperature, humidity, abundance of cloud droplets, they use this empirical equation to calculate this cloud to rain conversion rate. So this figure is from Shi et al. 2009. And x-axis, you have liquid water content that represents the thickness of clouds, and y-axis, it says autoconversion rate. You can roughly think of it as a conversion rate from cloud droplets to rain, and on log scale. And different curves show different parameterizations that are commonly used in numerical models, such as cloud resolving models or climate models. You can see that depending on which parameterization you use, the resultant autoconversion rates or the conversion rate from cloud droplets to raindrops can be significantly different. So, depending on which one you choose, the resultant cloud mass and rain mass can be eventually different too, because the rate is different. So if you go to the next slide, I added 2 more simulations or models. So a little coarser than cloud resolving models is cloud system resolving simulations, and also importantly, global climate models, GCMs. Their strength is the global coverage, of course, but at the same time, a lot of them cannot resolve convection, and convective clouds need to be, first of all, parameterized, and of course, the raindrop formation within those convective clouds need to be roughly estimated and parameterized as well. So if you go to the next slide, I'm going to be talking about what I did in my study. So we cannot afford this BIM microphysical calculation in CRMs or GCMs, but if we run a number of Parcel model simulations with BIM microphysics and then train a machine so that machine can learn the raindrop formation rate as a function of surrounding conditions such as temperature, humidity, etc., then we can use this trained machine in CRMs, and GCMs. So even without actually doing the bin microphysical calculations, they can still get similar raindrop formation rates as similarly as possible to what's actually calculated in those Parcel models. So this is the idea of this study. And today I'll tell you how I machine learned the Parcel model simulations and also how I implemented it in a CRM. So you can go to the next slide. And now I want to talk a little bit about this Parcel model that I'm using. So it's a Parcel model because it's literally simulating one parcel that is rising upwards at a constant vertical velocity. And as it goes up in the air, it expands and eventually it gets saturated and creates cloud droplets within it. So this Parcel model that I'm using is named Parcel. That was developed by Jiang and also his student, former student. And so the constant vertical velocity, and at the beginning, there are only aerosols. There is no cloud droplets at the beginning. And this Parcel model originally didn't include collision coalescence process, but I included it. And like I said, it's a bin microphysics that is used in this Parcel model. So there are more than 100 bins that represent the size distributions of aerosols and liquid droplets. So this is a very computationally expensive run, and it took around 2 or 3 hours to finish a 30-minute simulation just for one simulation. And at the bottom, I say initial conditions at 99% relative humidity, because if you go to the next slide, because the simulation starts at 99% relative humidity, subsaturated condition. So there is no cloud droplets, but this initial state was characterized by 10 different variables. Those 10 variables are temperature, pressure, vertical velocity, which is constant, and eddy dissipation rate epsilon that characterizes it's a representation of a turbulent nature of the parcel. So the higher it is, the more turbulent inside it is. And also size distributions of 2 different aerosol types. One is sulfate and the other is sea salt. So both of them follow a log normal size distribution. And so number and mean radius and geometric standard deviation. So those 3 characterize the log normal initial distribution of these aerosol particles. So these 10 variables were used to characterize the initial condition. And in order to obtain 1,000 sets of these 10 variables to run 1,000 simulations, I used the so-called the Latin hypercube data sampling. So for each of these 10 variables, I assumed a certain range and certain distribution, such as uniform or exponential, depending on the variable. And then once the PDF or CDF were given for each variable, 1,000 sets of these 10 variables were chosen through Latin hypercube data sampling. It's a little complex, so I'm not going to go too much in detail today, but this sampling allowed us to collect 1,000 sets of data very randomly, but based on the distribution of each variable. So if you go to the next slide, I'm showing an example simulation. So x-axis, I'm showing radius on log scale. Y-axis, I have time. So it's a temporal evolution of cloud droplet size distributions. And y-axis, we have mass density function. So it's abundance in terms of mass. Originally, there was only condensation in the Parcel model, so which was blue. So over time, it grows very gradually, but in a rising parcel, but it was very slow. Whereas when I included collision and coalescence, the size increase was much more rapid and dramatic. And so you see the rapid growth of droplets through collision and coalescence. So that's exactly what we wanted. So now the model includes collision coalescence. We ran thousands of these simulations. So you can go to the next slide. And you can, yeah. So I ran 1,000 of these simulations, and each of those simulations output temperature, pressure, supersaturation, and vertical velocity, eddy dissipation. Those ones in the brackets were constant throughout the simulations, and droplet, most importantly, droplet size distributions. So from these this droplet size distribution, I was able to get rain mass tendency dqr dt and rain number tendency dnr dt. And so those were what we wanted. And so for our study, rain is defined as droplets having radius larger than 100 microns. And then, so these top variables were used as input features in our machine learning procedure. And the bottom 3 or 2 variables were used as target. And then I say input features bracket 20 because actually there are 20 variables. I'm listing 6 only, but the bottom one is actually split into 15 different variables depending on the size. So there are 20 input features, and for target, it should be 1 for each machine to train. So for rain mass tendency dqr dt, I trained the machine number 1. So it learned dqr dt as a complex function of 20 input features, whereas machine number 2, it learned dnr dt as a complex function of input features, 20 input features listed above. So if you go to the next slide, I'm talking a little bit about the structure of the trained machine. So the structure of the trained machine is so-called multi-layer perceptron MLP. We start with 20 input features to the left, represented by blue circles, and they are connected to 20 neurons in the hidden layer number 1 in green, and in turn, those values are connected to 20 neurons in the hidden layer number 2, and eventually they're connected to the target value, which is either dqr dt or dnr dt. So what do I mean by they're connected? So each of those lines actually represents the weight value that's carried by the previous neuron to calculate the next neuron's value. So even though it looks complex, practically speaking, this structure of MLP is a complex polynomial, and that is very convenient for implementing into a weather forecasting model later on. So if you go to the next slide, I am talking about the machine predictions and their accuracy. So I know there are a lot of plots, but I want you to look at C, the third column at the top row. That is from MLP. X-axis, we have what's actually dqr dt, the rain production rates calculated by the BIM model. So it took a very long time to calculate because it's sophisticated based on BIM microphysics. And on y-axis, we have what dqr dt, the same variable predicted by the trained machine, having the structure of MLP. And I'm showing the frequency distributions by colors. So you can see that the highest frequencies lie on the x equals y line, meaning that the trained machines were able to predict dqr dt very, very similarly to what's actually calculated by the BIM model. And I also trained 2 other machines having different structures. One is called random forest, showing shown in A, and the other is gradient boosting, shown in B. They also had a good prediction scores. But when it comes to actually using this machine in a weather forecasting model, MLP was the best for the practical use. And yeah, there are also other plots from D to L. I'm showing what's predicted or prognosed by the commonly used parameterization for raindrop formation. So those are commonly used in weather forecasting models. And you can see that they diverge at some point from the x equals y line, meaning that they are different from what's calculated by the BIM model on x-axis. So what we did was replacing these parameterizations with this new trained machine shown in C, you having the structure of MLP. So if you go to the next slide, I am talking about the implementation in a model. I have to say that we're still at the testing stage. So today I'm going to just show you idealized simulations where this trained machine was actually used in those weather forecasting models. So this CRMs that I talked about earlier, the cloud resolving model, and so it's a weather research and forecasting model, WRF as a CRM, and I use the Morrison two-moment microphysics scheme, and the very default version where cloud droplet number concentration number was fixed, whereas DQR DT, change in rain production rate in terms of mass, and DNR DT in terms of number, they were replaced by the trained machine number 1 and trained machine number 2. And so the test cases that we looked at, there are 2 cases. Case 1 is idealized warm stratocumulus clouds, and number 2 was idealized supercell storm that is schematically shown by this figure by Klemp et al. 2007. But today I'm going to be mainly talking about case 2 because I haven't finished analyzing the results from case 1. But yeah, the distinction between the 2 cases are is that case 1 is only warm cloud processes. There's no ice phase involved, whereas case 2 involves all the processes. So I have to also mention that this machine learning based parameterization, or the machine itself, was activated or active only under certain dynamical conditions. For example, a temperature between -12 degrees Celsius and 20 degrees Celsius. The reason for that is because these trained machines were excellent at predicting DQR DT or DNR DT only within the range they were trained on. So they were not good at extrapolating their predictions beyond the ranges they were trained on. That's why, for example, temperature above or below this range, we used the original parameterization for DQR DT and DNR DT. So if you go to the next slide, I'm very briefly talking about the case for case 1, which I don't have much results for today. So it's actually a large eddy simulation, and that's why it's taking a very long time to finish. 100-meter horizontal resolution, 39 vertical levels, and the top is only 2 kilometers. So this is very typical, or even coarse for large eddy simulations. It has a fine resolutions in general. And shallow convection was triggered, and there's no radiation. You can see in this figure, I'm just showing a snapshot of a meridional mean cloud mass concentrate mixing ratio in grams per kilogram, and in the default control case. And I want to see how this cloud can be different if I use the machine. We are still analyzing that. But next slide, I'm talking about the supercell case. Again, it's a case that's given as a test case for all the WRF using user community and as a quarter circular shear supercell case. And convection was, so it's a originally very conditionally unstable environment. And convection was initiated by giving a thermal perturbation in the lower troposphere. And so it's a 2-kilometer horizontal resolution. So it's no longer a large eddy simulation, but it's more cloud resolving simulation for 40 vertical levels. And it was conditionally unstable. And there's no radiation at the moment. And because it's a supercell, it moves horizontally and eventually moves out of the domain around in 2 hours or so because it's on open boundary conditions. So if you go to the next slide, here I'm showing a snapshot after 15 minutes after the initiation of QC cloud mass in grams per meter cube in the left column, and the same but for rain mass on the right in the right column. And the top one is the default or original or control case. And the machine learned, the bottom is using the trained machine in estimating the imperfection rates. Only just after 15 minutes, you can see that there are some differences. For example, QC is less in the machine learned case, whereas rain mass QR is larger when the trained machine is used. And actually, this character of having less clouds, more rain, this pattern actually is retained throughout the simulation. So if you go to the next slide, I'm showing an hour after the initialization. And you can see that if I use the trained machine instead of the original parameterization, there's less cloud droplets, but more rain, as you can see on left and right respectively. So this actually continues until the end of the simulation. If you go to the next slide, that is showing after 2 hours. So around 2 hours or so, the convective core, main core, starts leaving the domain from the right side. So it's moving from the left to right. And you can see, again, less liquid cloud on the left side, but more rain on the right side, more or less, because it starts leaving the domain when I use the trained machine. So yeah, so instead of looking at those snapshots, I wanted to see the temporal evolution of it. So if you go to the next slide, I looked at the Hopmoller figure, so-called. So these are on the left, I'm showing QC, on the right, I'm showing QR. These are horizontally averaged QC and QR and its temporal evolution as you go from left to right. So x-axis is time in hours, y-axis is altitude in kilometers. And you can see, if you compare the two and see the bottom comparison, it is very clear that cloud mass QC is reduced when I use the trained machine in predicting rain production process. Whereas QR, there is still, it increases at the beginning, but it gets reduced afterwards. So I think I want to say two things. One is that it's probably, in terms of rain, it's probably more of a differences in the peak precipitation. So precipitation, the peak intensity occurs much later in the original simulation. That may be causing this negative difference. And it also, I have to mention that after 2 hours or so, the main core starts leaving the domain. So I'm not entirely sure if after 2 hours it's still a fair comparison. But generally speaking, this reduction in QC when I use the machine is a very encouraging result, because a lot of times those parameterizations that are commonly used in cloud resolving models, they have this problem of starting precipitation too late compared to observations. So having precipitation earlier, and also this conversion from cloud to rain is quicker, is very good news actually. But if we want to know which is right, we have to have observation and look at real data case instead of on this idealized case. So if you go to the next slide, I am looking at the surface accumulated precipitation in millimeters for the original default control case and the case where trained machine was used, and the difference between the two. You can see the difference is mostly positive, meaning that when I use a trained machine, precipitation increased. And if we look at the rainfall rate in millimeters per hour and also accumulated precipitation in millimeters, at the bottom two figures, you can see the earlier onset of surface rainfall when I use the machine learned parameterization or trained machine in the simulation. And you can also see around after 2 hours or so, rainfall rate starts reducing. That's exactly because convective core starts leaving out of the domain. And accumulated surface precipitation as for 2.5 hours that we looked at, precipitation is the total precipitation amount was larger for the machine learned case, but it is hard to conclude because we didn't simulate the entire life cycle of a supercell storm. But this earlier onset is is a finding that we made over the past week or so. And if we go to the next slide, this is my second last slide. But the next step is the application of this trained machine or trained machine parameterization in real case simulation or real data simulation. So all those two cases I just briefly introduced today were both idealized. So there's no observations that I can compare against. But if we can simulate a real case, real data case, preferably for maybe warm stratocumulus clouds with good observations of mass and number of cloud droplets and raindrops, I'll be able to conclude, okay, this trained machine actually is better than the existing parameterizations or worse. At least we can conclude that. So if we're actively looking for a good case where those observations were made, hopefully over the ocean so that there's no interference with urban heat island or those things. But if you know any good case with a good observational data sets, please let me know. And the next slide, I am summarizing all the findings. So physically based calculations of droplet to raindrop processes, so BIM microphysical calculations, were done in the expanded Parcel model. And it was done with 1,000 different sets of initial conditions, and the simulations ran 1,000 times. But because the output was given every second, the total amount of data that we looked at was more than 1 million. So data from 1,000 simulations, which translate into more than 1 million data, were used for training a machine for each of the targets. And this time the targets were DQR, DT, DNR, DT. And we saw high prediction scores, and MLP was most practical for implementation in WRF. And this MLP-based parameterization or the machine prediction showed enhanced rain formation or earlier rain formation in the convective supercell case. And to be done is the application in real data simulations. So the next slide is references. And thank you so much for giving me this opportunity. And I would like to welcome any questions and comments.
Okay, perfect. Thanks a lot for this very detailed explanation of the process. We have a first question in the Q&A from Alain Leger, who asked what are neurons and how does the learning machine work? So I think that,
Okay, well, so if you maybe can go back to the structure of NLP, that is slide number 16, I believe.
there we go. Oops, I clicked too many times, sorry. There we go.
Yeah, so 20 input features, they are normalized into values between 0 and 1. And those values are used to calculate, and then are used to calculate the values in these 20 neurons, or you can think of them as neurons as just values. And then those values are carried on to the next values through different weight values. So this line represents a weight, and then eventually goes to target. So initially they give some random numbers, random weights, and then calculate, goes through this process and get to the target value. And then they tweak these weight values and then try to get to the target value, to a better target value, because this is a supervised learning. So we know the answer dqrt. So the machine itself learns from its mistake, and then tries to correct those weight values and then change those weights so that it can get to the target value as closely as possible. So it goes through this training again and again and again until it reaches the very high, until the target values that they calculate is very close to the answer that we have, which is dqrt. So I know this sounds very maybe unclear, but neurons are, you can think of them as just values. We use input features first, and then they create some new set of 20 values in hidden layer number 1, and they are used again to calculate different values in hidden layer number 2, and they're calculated to use final target value. So how do they calculate? So this is again a polynomial. So they have a weight value. So it could be 0.6 or it could be negative 0.7. And then so they calculate again and again and again until they reach, okay, this prediction is close enough to this target value. And they do that for 1 million data sets and create, and then finally come up with all different kinds of weight values for each of these lines. And yeah, so eventually this is just super simple polynomial addition of different values or neuron values in hidden layers and input features. I hope it's clear. If it's not, I can explain in more detail later somewhere. But
yeah, okay, so thanks a lot, excellent. It's of course very difficult to explain deep neural networks in just a few words. So I know that these computations are very, very computationally costly. So how do you actually manage to implement that in an even more costly overall simulation? I think that's quite unique what you've done here.
yeah, so do you mean the computationally expensive? Do you mean the BIM model calculation or something else?
I mean normally you take some equations like A plus B equals C, something like that, and you put it into a model. But now you have a complete network that you with which you replace several equations. But still, I guess this network to compute it might be more complex or more demanding than just doing 10 equations and giving them to the computer.
Yeah.
So.
Yeah, that's actually an excellent point. I wanted to talk about it, but I forgot to mention. So, so I don't have an exact number right now, but when I ran this, just a default simulation, and say it took 5 minutes, then maybe for this one using this trained machine, it probably took 3 or 4 times more, because instead of using just one equation, just like you said, instead of just one equation, it goes through this machine, so it takes much longer. But we are still optimizing, trying to minimize the computational cost by changing the coding. And also, I have to mention, like I said earlier, if we try to use the BIM model, that is going to be much more expensive than just 3 times more expensive, because for running one grid for 30 minutes, it took 3 hours. So if you can imagine implementing it in cloud resolving models, it's going to be very extremely expensive. It's not affordable. So yes, the computational cost is still more expensive than the original run, but when you consider having the accuracy of BIM model, that it is still relatively cheaper cost. So yeah, so it's still expensive, but considering the outcome that is accurate, yeah, it is. I believe it is worth it, and we're still trying to minimize computational cost by changing the code a little bit.
Yeah, looks great. So it's really this model with 2 times 20 neurons that you use, but not a more complex, because in the plankton image classification, what I work, well, the models are sometimes really huge and much larger, with much more layers and much more nodes.
Okay. Yeah.
Oh, okay, good. Then Subbu actually raised his hand. Subbu, please.
Yeah, thanks for that interesting presentation. It's so sorry if I missed this, but what was your, do you have an explanation for why the machine learning algorithm, I think it underpredicts the cloud cover and overpredicts the rainfall? And do you have an explanation for that? Sometimes these machine learning models are kind of black boxes and you don't understand exactly what's happening, but you would hope that there is some physical reason why they are picking that up or why they're biased in a particular way. And do you have a way to correct it? Or what is the plan to correct it?
Yeah, okay, well, that's an excellent question too. And yeah, if you can go to the slide number 24, it's case 2 supercell. Yeah, that's perfect. So first of all, the top one, original, is it uses some simplified parameterization that is not necessarily the reality. And then I would consider the second one that's using the machine is closer to the reality, because it's based on the parameterization that is very complex and coming from the BIM model calculations. And to answer your question, so at the bottom, why is there such a tendency? Well, so I think there are several theories why those parameterizations in the top row, they produce rain later or less than what it's actually supposed to be, because I think those small turbulences in the air parcel can actually enhance collision between small cloud droplets, but that are often not well reproduced in lab experiments, but those parameterizations in the top row, they are a lot of times based on just simple observations and just deducing the rate from the observations, or simply through lab experiments. So, but in reality, there's a lot of turbulences that can actually enhance collision coalescence and expedite or enhance the creation of raindrops. So, but that can be only realized in very detailed models, such as direct numerical simulations or BIM models that I base the machine learning on. So that's why in the machine learned case, the second row, there is earlier onset of precipitation because this turbulence effect is included. So there's enhanced collision coalescence likely compared to the original bulk parameterization that is probably based on just observations and then deduce the rate from concentrations or lab experiments where there were not much of turbulence. So that's my guess, and I think there can be more explanations. But
thank you.
Excellent. There further questions? Not, I maybe have another one. I mean, I can also go back to the slide. Actually, slide 17, you show these results that that the predictions by the trained machines are much better than the other algorithms. So, but these other algorithms are they don't have the detailed physics in them, right? And that's why you think why they are much worse.
Sorry, they don't have detailed what?
The physics of the BIM model in it,
yeah.
right? Mm-hmm.
Well, yeah, some of them are more sophisticated than the others. For example, I think the simplest and the earliest one was Kessler, I'm showing in D, which is very simple. If the cloud mass is larger than this, then like linearly proportional to the cloud mass create this much rain. Whereas I think the bottom four, or from H to L, they're based more on, originally maybe they were based on BIM microphysics, or probably not. I don't remember the details, but they were somewhat more physically based rather than Kessler, for example. So there is still a huge variation among these two. And for example, if you compare Kessler D with L, then maybe L is doing much better in terms of predicting D2R, DT. But if they're physically based or not, I have to look into their detailed parameterization again. I actually, at the moment, I don't remember the details for each of them, but some of them are more physically based than the rest. That's all I can say right now.
And in which range is it important for these models to be correct? Is it like on the right side or on the left side? I mean, if they are correct on the right side and the left side is not relevant, then that doesn't matter, right?
Because the numbers are small.
Yeah, or I don't know anything about the physics really shown here, but if the clouds don't exist that are on the left side, then it wouldn't matter. I don't know. And so to some extent, the question then is also, if these models are so bad, what is about the modeling of rain on Earth in IPCC models and these things? Does that work at all, or is it very far away from reality?
Yeah, well, in terms of the importance, importance is lying to the upper right, of course, because that's where the highest frequencies are. But so if we just want to look at the rough numbers, I think someone can argue that using those parameterization is cost effective, like computationally cost effective and good enough for the those upper right ranges. Yes, I think that's true, especially when running a climate model or something. But when we want to be very accurate in terms of the amount of precipitation or rates, then yes, these machine learned parameterizations can be very powerful. And I think, yeah, so I hope that answers your question.
Yes, very much. Thank you. Yeah, if there are no other questions, then I have one last from my side. I'm very curious today. So You said at the end that you need measurements from the ocean. What measurements does that mean actually?
Yeah, so I believe, yeah, the third last slide. So, yeah, I want a measurement of cloud droplet number concentrations and their mass, and also rain number concentrations and their mass, because today I showed all the idealized cases, but we can't really say which simulation was closer to the reality. That's why all the variables that I showed today, compared simulations with, I want those variables from observations and try to use real reanalysis data set to initialize the simulation, and then see the simulations that I ran with the trained machine are actually better in predicting QC and C and those variables. Because if not, then having higher computational costs and worse results, we don't want to use that module. So we want to make sure that using that trained machine actually enhances or promotes the accuracy of the simulation. So that's why I want, yeah, those number and mass concentrations of cloud and rain, particularly over ocean.
And how can they be measured?
Oh, how can they be measured? Oh, they can be measured by, for example, there can be ship measurements, or they can be aircraft measurements through during field campaigns. Yeah, so actually, I'm looking for some field campaigns that provide this set of data sets. And I have a few in my mind, but I'm not certain at this point. But yeah, those aircrafts can measure those variables.
Yeah. There was actually a big UREC A4, I think it's called, experiment nearby Brazil 1 or 2 years ago with 4 research vessels. That might be interesting for you. I can look into the details.